All right, let's get started. So today I want to try to dig into the storage hierarchy for a multi-threaded execution. So you have threads running on multiple cores, and like what actually happens as we write to a memory address. And it's a relatively thick stack, so we'll see how far we get into it. There's a lot of complexity in there. I have two of the reference manuals up here, the 3500 manual, 3500 pages, and then the other one here for 788 pages. They're not all about memory accesses, fortunately. Most of it is just like, this is how the instruction works. But yeah, I found some real gems in there. I thought we would, toward the end of the class, spend some time just reading through some of the examples and maybe try to run a couple of, actually run a couple of programs to demonstrate the weird effects that you can get. But so maybe first, fact, I think there was a nice picture here somewhere. No, it was somewhere else. Yeah. Anyway, so let's see. We have threads running on at least on two separate cores, and they are accessing the same piece of memory, and we want to kind of see what is it that each core is doing to fulfill a read or a store. So let's start with a read. Actually, usually you would call them a load, I think. So there's lots of, assuming we're in assembly land here. Like the compiler can do things for you as well, but let's ignore that. So we have assembly instructions. The instruction says load from this address into this register. That's it. So what do we do? Well, I think first of all we'd have to figure out where it is in memory. I think if you've taken 361 or 461, you might be familiar with the page tables. Who feels familiar with how page tables work? Okay, I would hope you're familiar. Okay, good. So maybe half of you. So let's just briefly review that first then. So first you have okay, so we say address into register. All right, so there's one little piece where the register, we actually have to find a slot in the register renaming table. Let's ignore the internals of the actual core and just look at the memory hierarchy for now. So starting out, this is actually a virtual address. All right, so this refers to the process's address space. You may have noticed that every time you run a program, the pointers, if you print out a pointer, they always kind of look the same. Right? Usually, a function pointer would be pretty low numbers, in the tens of thousands, hundreds of thousands, something like that. And then your stack would be starting maybe with a 7 FFF or something like that. And so every process has its own view of memory. It looks to the process as if there's nothing else there. And so we have a 48 or 47-bit memory range that the process conceivably could try to read from. Right? If there's some memory actually allocated to the process, the read would succeed. Otherwise, you end up with a segmentation fault. Okay, so the first step is we need to go from virtual address to physical address. So a physical address is basically just an index into all of these chips. Right? You have these memory chips sitting around, depending on how your machine looks. It might be a few, or it could be like 100 of them. And each one of them has so many bytes in it. Right? The physical address says exactly which one. Actually, I might be exaggerating a little bit, but let's use that simplification. So, all right. So we go from a process virtual address that says 100, and every other process also says 100, like they want to access their 100, but they all have to be different hundreds, but we only have one set of memory. We have 1,000 pages of memory, 4 megabytes of memory, let's say, and every process tries to access the same piece, the same address, but they all need to see different contents. The processes should not be communicating with each other. The way that works is it goes through a page table, which is basically a lookup table of virtual page number to physical page number. And by page, we usually mean 4096 bytes. So the physical memory is divided in these 4K chunks. They all get a number. Basically, you ignore the lower 12 bits of the address. There's your page number, right, for physical address. And the same thing for virtual addresses. So you see, okay. So actually, I should write this. A virtual address, an address might look like page number, and then 12-bit page offset, right? So it's the same both for virtual and physical pages. So if a process needs a little more memory, the kernel can bestow it upon the process by adding an entry into this lookup table, saying, okay, your virtual page number 4, that would be address 16,384 and up, right? 4 kilobytes up. That is now populated. So if you try to dereference some of that memory, the CPU will find it for you. So we could imagine a page table looking like, it's actually not quite a lookup table, it's closer to an array maybe. But anyway, so we could say that, oh, page 0 for this process is page 102 of physical memory, and page 1 is page number 200, and page 3 is physical page, sometimes we call it a page frame, number 66. All right, so using this kind of page table, we're able to map different parts of the memory, the physical memory, into what looks like a contiguous range of virtual memory addresses. Here we mapped in 3 different pages from all over physical memory, and it looks like, oh, I should put a 2 there. It looks like 12 kilobytes of contiguous memory. Generally speaking, this is how all memory works in any OS or any architecture that you're dealing with, except for some embedded architectures where you don't have an operating system. Generally speaking, you need these virtual addresses in order to provide process isolation and just the sort of security guarantees that an operating system can offer. Okay, so we need that, but in the end, how this actually is managed, that's up to the operating system. Like how we set up the page table, that's up to the operating system. We play a lot with that in the OS class. So let's not worry about that. The layout in memory of the page table, it's not actually a hash table. I say lookup table, it kind of feels like, oh, that's a hash table. It's not. It's a tree of arrays, 3 of 4096 byte-sized arrays. That structure also isn't that important for this class, tremendously important for the OS class. We can think of it as a lookup table, but it's kind of slow to find the right address. So you're saying, oh, let's move like this address, global variable A into my register, easy, right? Just go and get the memory, but unfortunately, it's not a physical address, it's a virtual address, and the only way to find out the actual physical address is to look in 4 other places in memory on a 64-bit machine. There's a tree of depth 4 or sometimes 5, I think, that So you go through the root of the tree, and then the next level, and the next level, and the next level, and finally you found your index on this thing in the virtual, in the page table. So that sounds slow. Right? It's 4 memory accesses just to do 1 memory access. And the solution that most chips will have is called a translation look-aside buffer. It's a page table cache. So basically, it'll have room for thousands, maybe. Well, I don't know the size of it. Thousands is probably a little much. Maybe 500 to a couple of thousand entries like this. So the cache will remember. Oh yeah, virtual page 5, physical page that. It won't have the whole page table in it. It's one thing we could try maybe later today. If we allocate a lot of memory, we'll find that for particularly large amounts of memory, where this cache can't hold all of the page table entries that we're using to access the different parts of this memory, suddenly the memory accesses get slower, even though perhaps it's big enough to be in the cache, in the memory cache. Maybe we can come up with an experiment for that. Okay, so fortunately, this one is really fast. It can do 3 of these lookups per cycle, so we don't really need to worry about it. Well, it can do 2 load lookups and 1 store lookup. I don't know why there's a difference. But anyway, we go from virtual address to physical address. We need to look through this translation look-aside buffer, and if our address that we're looking for is not in there, well, then it's going to be slow. And then in the best case, it'll be 4 accesses to our L1 cache, so 16 cycles. And generally speaking, you would be lucky if that's the case. So you're probably looking at potentially hundreds of cycles. One more reason to have nice local access for in your code. Right? The L1 cache is one restriction, but the size of the TLB is another restriction. Not something you usually run into, or at least usually think about. It's also the case that whenever you switch processes, if you're doing a context switch, you lose all of that. It would get really confusing if the TLB held the old page table entries from the previous process, right? It was mapping in some pages from another process, and now your variables suddenly are holding the contents of the other process's variables. That would be weird. So the only way to get this to work is to clear the cache, or potentially somehow track a process ID in the cache, but processes don't exist from the point of view of the processor. Right? The processor only runs a sequence of instructions that it's told. That's that. Yeah. So when you switch processes, you end up with a bit of a hit from that too. In fact, that might be. I wonder if we can measure that. Seems hard to measure, but I'd like to measure the latency of a memory access the first time after a process switch. Right? You access memory one time, it should be longer than the next time you access it. But it's really hard to measure at cycle granularity, measure exactly at cycle granularity. But maybe we could do something like that. That would actually be a cool homework to set that up. But, okay, so we've gone from virtual address to physical address through the TLB. So now we have a physical address. Now we need to see, well, do we have it? Right? Do we have it in our data cache? So we check some caches, right? We check the L1. That's the one that's the closest. That's 4 cycles. We check the L2. If it's not in the L1, we check the L2. If it's not in the L2, we check the LLC. If it's not in the LLC, we potentially, if there's more chips on this machine, we'll have to check the other sockets, LLCs. So we could call those remote LLCs. And if it's not there, then finally we go and fetch it from DRAM. Okay, so we're doing a load. Loads are maybe a little bit easier. So if an entry exists anywhere in one of these, then we can use that value, generally speaking. So you might imagine that, well, maybe someone has written to this, like this is a cache value. Cache values get stale. Like a web cache or something, maybe you've noticed sometimes you have old values sitting around, you have to reload your browser for things to look right, or Same thing here. If we find an entry in here, we'll use it. But it's not clear that it's a recent value. It's got to be somewhat recent. But there's no guarantee that whatever's sitting in the cache when we're doing a load is actually the most recent thing written by another store. By a store by another CPU, that is. There is a guarantee for our own processor. It's actually guaranteed, and we'll see how that works in a little bit. Okay, so we'll look through all of those, and any cache entry in any state, see the states in a bit, will be fine. Okay, and I think that's roughly it for a load. But the complicating bit here is the fact that it's stale. We need to keep that in mind, that it could be stale. Yeah.
The remote LLCs, isn't the LLC shared by the cores?
Within one socket.
Within one socket.
Right.
Okay.
So you could potentially have multiple sockets in the machine, and then they have an interconnect, and there's a little memory controller that is in charge of asking such questions. Right. And that's also true for the DRAM, right? It's not necessarily connected directly to the chip that we're running on. It could be connected to a remote chip, and then the memory controller will send a request over to the other side, and it gets read there. Fortunately, we don't have to see the effects of this very much, but you can sometimes see it in performance measurements, as always. All right, so let's think about a store. And we'll look at ordering and such in a little bit. First, we have to see how these things work. So for a store, it's the same thing. Oh yeah, so this is actually kind of an interesting observation, I suppose, maybe. These caches, these are actually physical addresses. There's a benefit to that. If they were indexed by virtual address, when you switch processes, you'd have to clear the whole cache. But in this case, if you switch between processes, we clear the translation look-aside buffer, and then this new process won't be able to access those physical memory pages anyway, because they're not mapped into its address space. So we can keep all of the caches the way they were, and that's probably why they did it this way. Okay, so for a store, again, virtual to physical. No difference, except it might, the processor here will see if we're allowed to write to the page. And so for a load, it's only a question of, is there a page in the page table? Like, does that dictionary have a valid mapping for the page we're trying to access? For a store, there's also the question of whether we're allowed to write to it. If not, there will be a page fault. We get the CPU and the operating system will be in charge of deciding whether to kill the process, whether to put a page there where it wanted to access, and so on. Another OS topic. Okay, so now we have a physical address and we need to check the caches, but it's a little bit different now. Because if you want to store, you can't really just store into your cache and hope for the best. Right? But generally speaking, we would want any other CPU that loads from this address to get our value. Right? Well, we can't guarantee that they're using these kind of just loads and stores. We can't guarantee that they will always get their value right after we wrote it. But at some point, they should get it at least. And if you have two processors making stores, now it starts getting extra complicated. Let's see. So say we have two variables that are sitting in the same cache line. You have a x and a y. They're in the same cache line. Processor 1 writes to x. Processor 2 writes to y. Right? So now, what's going to happen? Well, you could imagine that both of them have a copy in their L1. Let's see, actually. Okay, so P1 writes to variable x, processor 2 writes to variable y, and they're both in the same cache line. So you could imagine that this cache line is in the L1 cache of both processors. That's actually perfectly fine, as long as all they've been doing so far is read from this 64-byte chunk. Remember, the caches all deal with 64-byte chunks. As long as all they do is read from this chunk, they can both have copies, and they're read-only copies of this cache line. So now they want to write to the cache line. You can imagine maybe two possibilities. One would be they both turn it into a read-write cache line, right? And then they just make their write to each one variable. Now we have this problem with two copies of the same cache line that have different contents. That would good. One could maybe imagine kind of tracking which parts got written to and trying to merge them later or something, but it's really not how you want to do things. So what the most CPUs require is that if you want to write to a cache line, the cache line, it can't be in read-only mode. It needs to be in writable mode, but the only writable mode that exists is exclusively writable. So if you want to be able to write to this cache line, it has to be yours alone. There exists no other copies of this cache line in the system, and certainly no one else is trying to write to it. Okay, so these two processors are trying to write, so what happens? Well, they need to acquire the cache line in exclusive mode. And again, this is only what happens under the covers, right? I think as a programmer, you cannot directly even see the state of the cache line. You certainly can't modify it other than trying to write to a cache line, and then it'll become exclusive writable mode for a moment until another one of your cores tries to access it. Okay, so let's see. So there's modified. There's several. So this is a common sort of set of states that cache lines can be in. Might as well list them. So there's modified, owned. I don't know what owned and what the difference is between owned and exclusive, honestly. So let's put those two together for now. Shared and invalid. All right, so they're kind of self-explanatory. Modified means I own it, but I changed it. So now if anyone wants to read from this cache line again, and when I say cache line, I'm actually referring to a 64-byte chunk of the physical memory space. Right? It's not that it's sitting in my cache at the moment. It's this specifically identified 64-byte chunk. if anyone wants to to access that chunk, they're going to have to get it from me. Because if they get it from DRAM, it's old stuff. Right? You can also be in exclusive mode. This means, oh, okay. Maybe it's, I'm going to make a sort of an informed guess. Let's see, let's do it like this. Oh, it's an unfortunate order, but okay. So before you write to anything, this cache line has to be in exclusive mode. So you first have to inform everyone else that they cannot have the cache line, and they have to tell you that okay. Because otherwise, you end up potentially both of these two processes writing to the same cache line at the same time, and we might have a problem. We don't know which state the cache should be in. Right? And then when you want to write it out to memory, you don't know what's the right version and so on. So that's how they try to manage this. Okay, so before you write to the cache line, you have to make sure it's in exclusive mode, which means there's coordination with all the other chips, making sure they don't have a copy of this cache line. You can see why this starts getting a little both slow and complicated, because there's a lot of coordination and the chips are potentially kind of far away. It's not a question of executing instructions. This is all happening at lower level. All right. I think, this is a guess, owned probably means it's read-only, but I'm the only one that owns it at the moment. I'm the only one that has a copy of it at the moment. Shared is also read-only, but there's multiple copies. So if you have the cache line in owned state at the moment, then you can very easily make it exclusive. You don't have to ask anyone else because they don't have copies yet, so that's fine. And if you're an exclusive, then you're allowed to write to it, make it modified. And if you own it, someone else might ask you for a copy of this cache line. If you look back at the list of what we're doing, right? We're checking all of these other places first before we go to DRAM. And the reason is the DRAM is both slow, but often has an old value. And there's no guarantee that the most recent version of the cache line actually is in RAM. It'll get written out eventually, either when you need to evict one of these cache lines from memory, then that's the only way. Basically, write out the contents if you have it in modified. If the CPU needs another line from the cache, it'll have to evict something. It'll evict one of your modified lines. That means it writes it out to DRAM. In all the other cases, you can just forget about it. Like it's not, you don't have the most recent version or the only recent version of this line, so it's okay to just overwrite the contents. And it can be invalid. That's what happens when you try to write. So we started out, let's take our running example. We had actually P1 and P2 had read X and Y in the past. Maybe, oh, this is good. Let's do like this instead. Right. So now it's a read and a write. So initially, it ended up in shared mode. Guess it depends a little bit, but let's say. So now they both are able to read it. And then they both want to write. Now they have to coordinate. So P1 maybe gets out first. It sends an invalidation message to P2's core saying, I need you to make the cache line invalid. Right, so on P2 it becomes invalid. On P1 it becomes exclusive. Then it increments it stores the incremented value. So now it's modified. And P2, because it still wants to store, right, it has another pending request. So now it asks P2's core for this modified line. It'll get a copy of the modified line. I think there's two ways they can do it. They can say request for ownership or request for a copy. but in this case, let's say it does a request for ownership, so then it becomes invalid on P1, and it makes its way over to P2, where it's probably owned or exclusive. And then we do the write and becomes modified. So that's the sort of the, yeah.
So in the case that owned would allow others to have copies of the value, but it would like have to, like I just looked it up, it would have to like share if it changed it.
Yeah.
Ultimately, how would that change things? You know what I mean?
Let's see. So you're starting at in owned, and someone else gets a copy because they want to read from it. Is that what we're saying?
The same, like essentially, if it's owned,
Yeah.
you have the right to change it, just you, but then other caches can also use it, but whenever you change it, you have to
Oh,
broadcast
I
it.
see. Okay, so I wasn't quite right there. So owned can actually be shared. It's just that you kind of have priority.
Yeah.
Yeah. So I would imagine that rather than a broadcast, if it's owned, if someone wants it to become theirs, rather than tell everyone, you probably tell the owner, and the owner tells the others. But yeah, this is too low a detail for me to give good answers. Okay, so anyway, this is going to take a while. All right, and worse than that, it's going to take a different amount of time, depending on what you're up to. So if you're trying to access a variable that is currently in, say, modified in your core, in your L1, in that case, it's going to be a really fast write, just 4 cycles. But if it's modified somewhere else, but then you have to wait until they send you the cache line. Right? And we don't know how long that's going to take. There could be other cores that are also trying to modify it. Maybe they got in first. So it could be a potentially long wait before you get this cache line. So that gives us the problem, because so far, our discussion of the CPU and its out of order execution says whenever we have a dependency, like a data dependency on an instruction, whenever that's been satisfied, then we run the instruction. So in this case, you could imagine, let's do a different example. Two examples. So we store to x equals 1, but x is okay. So this is fine, right? We run x, we run the store to x, that goes quickly, and then we run the store to y, and that will take a while. We don't need to worry about it. But you could also imagine a situation where it's the opposite. So if you want a sequential execution, and at least on a single CPU, we don't even care. Actually, yeah. Maybe we should. What can we do about that? On a single CPU, doesn't matter. Yeah. So here we're starting to execute this instruction, and then because we're running this parallel out of order execution thing, we also start running the next instruction because there's no dependency between the two so far. So in that case, this one will finish really soon, and then this one will finish in a few hundred cycles. And so why would that become a problem? In this case, maybe it's not so obvious, but let's try another case. Let's say like this. Okay. So imagine this situation. So, well, make it even clearer, I'll call it data is ready flag. Right. So I write some data first, And then after it's written, I say it's ready. So that another CPU can spin on this data is ready flag. And once the data is ready, it'll stop spinning and go and fetch the data. That'd be awesome. Unfortunately, at least under our current assumptions, this one's going to run long before this is done. Right? So now whoever's looking at this flag will think that the data is ready, but it's not. So this is what's called a memory consistency problem, I suppose. Or generally speaking, we need to know something about memory consistency models. This is a really hairy topic, and we won't do much of it, in part because I feel I have a tenuous grasp on much of it. But there's a couple of things that we probably would like to have. You could say a sequential consistency model. A sequential consistency model would say that, well, no matter what you run on all your cores, there is a way in which you could order these instructions so that the outcome, the instructions running on different cores, right? Such that you could have run it on one core. So you have all these instructions running in parallel on different cores, but you just kind of interleave them all in some way. It doesn't matter which one, but some way, without reordering the individual instruction stream. And if you can run it in some way on a single core and get the same result, then we have sequential consistency. And that's pretty great. Unfortunately, it's ridiculously expensive and nobody provides it. So what we get instead are various strange effects from the fact that we're running in parallel. And different CPUs will offer different degrees, different kinds of consistency, but because this class is very focused on x86, we'll talk about mostly what the x86 provides, or what Intel and AMD provide, really. Well, I guess there are some other manufacturers too. Okay, so on the x86, it's something called a total store order. Basically, that's not good. Total store order, like that. And we'll see the exact details in a little bit, but the most important, we'll see the exact details to the extent that Intel provides exact details, but it's more than we need in this class. The most important part of the x86 total store order memory consistency model is that any stores by a single CPU are visible in the same order by all other CPUs. So in this case, we may have been running this thing on one CPU. We may have been running these two in parallel, and maybe this one finished long before that one. But according to the memory consistency model, the CPU may not write this to memory, may not make this visible to any other core in the wrong order. So the data is ready flag has to show up after the data has been written. Okay, so how do we make that actually happen? Turns out we need a step in between here. So when we're running these instructions, we actually don't worry about the cache much. So whenever we're doing a store, we don't write it to the cache. Instead, it ends up in a store buffer. Let's see. Add the store to a store buffer. Okay, so we said, okay, write this value to variable x. But it doesn't actually go and write it to variable x. Instead, it just takes this job, like, oh, I need to write the value. It adds that into a queue, a first in, first out queue called the store buffer. And and leaves it. At the same time, sort of, the store buffer will then start trying to get the cache line. So we already finished the instruction. We already wrote this thing. From the perspective of execution, it's already a retired instruction. We're going to move on to the next instructions. Forget about this. Now the store is sitting in the store buffer in this FIFO queue. The store buffer is looking at the whole queue in parallel and sees, okay, I need all these cache lines. So it'll make requests for the cache lines to get them in exclusive mode. And whenever they show up, it tries to like empty its buffer. So we have, this is not such a good example. Let's see. Oh yeah, so in this case, let's say this is, the data is very small. So it's data is 8. The single write, make it easier. Like now we have 2 writes. Otherwise, if it's one of those big structs, it could be a whole mem copy. Okay, so in this case, this store goes into the store buffer first. This store goes into the store buffer second, and so now the store buffer will look only at the first one because it's a first in, first out queue. So it'll wait until this remote cache line has showed up in exclusive mode. Then it'll drain this entry. And then it'll look at the next one. Oh, we already have it in L1, let's go. Right? But it'll actually drain all of these stores in a certain order, in whichever order it came in. And the stores always come into the store buffer in the order that is written in the code. So we talk about how you can reorder things, but there's actually an sort of an implicit order, or no, maybe it's an explicit order. The order in the code, the order of the instructions is actually strictly followed by the store buffer. Like when you add things to the store buffer, it'll be in that order. Questions before we move on? Store buffer has room for, let's see. Some 56 entries in recent CPUs, if I remember correctly. So you can imagine 2 different ways that we could design this, right? You could go without a store buffer, and you just say, oh, it's a store. Like, never mind, we'll not reorder anything. Like, here's a store instruction, everybody stop until this store instruction has finished, and then we'll continue, right? But that would go really slow. We want more concurrency, so the reason that we have the store buffer is, in that sense, to make stores go faster. Or you could say we have the store buffer because otherwise this whole parallel machine, it wouldn't provide a total store order. Why do we want the total store order? Yeah.
The store buffer is maxed out, then we
and we stop. Yeah, the machine will basically, let's see, I think there's a counter for it. I forgot the name. But anyway, there's certainly performance counters that will tell you that it's stalled because of the store buffer is full. And it is a very important resource constraint sometimes. If you do a lot of writing, that's a huge problem. So funny effects that you can see is, let's say you work mostly with local variables or something that's sitting in your L1. But then you have one big faraway store. So now you're running your one faraway store first, and then a whole bunch of these local work, which should be really fast. And you fill up the store buffer with all sorts of assignments, and you're still waiting for that faraway store to finish. Now the store buffer is full, so your whole CPU is stopped. Not because you're doing so many remote accesses, but because you made one remote access that was quite slow, and then a lot of other stores to what should be fast L1 memory addresses. and it'll still hold you up. We've run into that quite a bit in my group. One way to avoid it is to try not to make so many stores. Right? If you keep it in registers, it's okay. Registers are never shown to other CPUs, so they're not subject to a memory consistency model. Okay, so what if there's a couple more things going on before we get to the specs. Let's see. Right, so yeah, so we put it into the store buffer, then asynchronously fetch the cache, and once it shows up, if we're at the front of the store buffer, the store actually makes it out. But what if, while one of those stores is pending, we make a load? Right? So I say x equals 5, and then move $5 to x, move x to Rx, right? So now this store is sitting in the store buffer. That kind of sucks. So it's going to take a while before it drains. It's got 55 other entries before it, and we're trying to make a load. And we have the value. I mean, we just put a 5 over there. So if this load happened on a different core, there's nothing we can do. Another core wrote a 5 to x, but it's just not visible to anyone. It already executed that. So in principle, if this was a sequential machine, no one should be able to load x again until this 5 is visible. But it's not a sequential machine. So if you're loading on a different core, you're going to get stale values. Always the case with normal moves and stores. But if you're doing it on the same core, then you actually get the recent value and almost immediately. So this actually loads from the store buffer. And I think it's something like L1 speeds. So it's not really a problem. Even if you wrote to some faraway memory and you want to read, for whatever reason you want to read it again, it's okay. Okay. Let's take a look at some funny effects. Actually, before questions. Yeah.
How does this thing work actually? Like, if it's like a FIFO queue, then lookups are not going to be very fast.
Let's see. Lookups. Oh, how do you do this thing with lots of hardware?
L1 speeds.
Yeah. How do they get that? It's I don't know how they make it fast, but the L1 is also complicated. Right? It's lots of different places where it's 8-way associative, so they have to check those 8. In this case, maybe it's a little slower than the L1, but it only has to check 56 places. So I think there are some exceptions, but now we're getting a little too detailed. Like if you say you write an 8-byte value at like 5 bytes offset or something. So you say like, write your 8-byte values to an address that ends with a 1. Right? So now it's not 8-byte aligned. It's kind of off by a bit. Those are slower because now it's going to be 2 different parts of the 2 different little chunks of memory that it needs to. Even worse. It could potentially even span 2 cache lines. Right? One store can span 2 cache lines, and that sort of thing apparently runs slower. But usually, we want to try to align our values to the size of the value. In the most recent CPUs, I think they almost eliminated the penalty for that.
Do we have to check the store buffer on every load then?
Well, yes.
If I load from the store buffer and then I want to write again against that
same memory address, does that create a new entry in the store buffer, or
Yeah.
does it overwrite the old one?
It'll be a new one.
Okay.
It could potentially eliminate the old one. That might be safe.
Okay.
But it certainly wouldn't be safe to overwrite, because then you'd kind of get a shortcut.
Right.
And now suddenly you're out of order.
Mhm.
Would it be safe to eliminate it? Probably would be safe to eliminate the old one. But, well, no. So you could imagine, like, I'm writing an 8-byte thing first, and then my new write is only a 1-byte write.
Okay,
Right? And so
Yeah.
you'd have to get the combination of the two at least.
that's true.
And then, yeah. Things are hard to tell what's safe and not. I would probably leave it, but it's not like you get to touch it anyway, so.
Okay. I
What-
was just thinking that something could be making a lot of writes,
Mm-hmm.
and it never leaves the store buffer while somebody else is trying to, or another core is trying to get control over it.
Oh yeah, so store buffer is unrelated to the caches really.
Okay.
So if you have two, and we should definitely run an experiment with that. You have two processes or two threads running on different cores, writing to the same cache line.
Mhm.
They will more or less alternate.
Okay.
So you might end up, if you have your store buffer full with stuff, full of writes to this one line, maybe it'll drain drain all of those before relinquishing the cache line, but it'll make it over to the other side. And yeah, there's some sort of alternating thing going on. There's no starvation, but yeah, there's no guarantees either that they will interleave perfectly or anything like that. Yeah. Okay, so I wanted to look at the guarantees first, just so we get a quick look at the sort of memory consistency model they provide, and then some examples that they provide of what can go wrong. Actually, I forgot. There's also the atomic instructions. I think we should discuss that first. So these are all normal loads and stores, and whenever you're communicating with another CPU, generally speaking, it's unsafe because of these reasons, right? Because things get out of order and so on. If you want to be safe, you will need to use, they're called atomic or locked instructions. The moves are actually atomic. Like a single move is atomic. But if you want to do an increment, that's a move, an increment, and a store. That's 3 instructions. And now things start getting a little iffy. Or a very common one is you want to see if this lock is locked, right? And what does it mean that a lock is locked? It means the value is a 1 instead of a 0. And if it's locked, if it's unlocked, you want to lock it for yourself. That's a very, very common operation. So in a lock implementation, you would imagine you have these two processors, they're both checking the lock, and they both see, oh, it's a 0, so let me take it. So if the lock is 0, next up, set the lock to 1, and now they both think that they got it. And that totally would happen in this scenario. So in order to be able to implement synchronization operations like that, there are these atomic instructions which basically do 3 things at once. So it'll read and then compare and then maybe set. That's a atomic compare and exchange. Or it'll read and increment and set. And during that time, we're guaranteed that no one else can execute the same thing. Someone else could store to this variable, but they couldn't execute an atomic instruction, an atomic compare and exchange, let's say, at the same time. So the most common ones are lock, exchange, and lock inc. You'll find that there's others. The point of these is that for a given memory address, only one can execute at the same time. So how do we implement that? Well, we have to, before we read from this cache line, we have to get the cache line in exclusive mode, and we have to hold on to it, make sure that no other chip gets the cache line back before we've written our new results. So we read it, we increment it locally, and we try to write it. Now it's in the store buffer, right? And that could take a while before it makes it out for a normal instruction. But with an atomic instruction, they kind of do it a little bit differently. So now you acquire, in order to do that, to start the read, you get the cache line in exclusive mode already, and then the cache line is marked that it can't escape, and then you do your write. It does end up in the store buffer, because all stores are ordered, atomic stores as well. But the cache line that you just read from, it can't change until you've finished your store. So this can really slow things down too, right? Okay, so acquires cache line in exclusive, read, holds on to it until store has completed. Okay, so there's some guarantees here. We already had a guarantee that all stores appear in the same order, and that's provided by the store buffer. For an atomic instruction, no instructions execute before no instructions move from after the atomic instruction to before the atomic instruction. So there's a constraint on the reordering. We should probably look at the specs for that. Okay, and then we have one more, and those are called fences. There's M fence, S fence, L fence. Those are instructions that say you may not run any instructions before this fence, after this fence, until all the instructions before the fence have finished. So this might be a good way for our, let's see, where's our example with the flag? So here is one nice way that we can fix this. In fact, here we have on the x86, the total store order already fixes this, but on an ARM it wouldn't. On the ARM you don't get that guarantee, so then you would have to put an M fence here, which guarantees that the data store has finished before the data is ready, store starts. And those are also really expensive. You can see why. We used to execute all these hundreds of things in parallel, but then suddenly we run into this fence. So now we have to drain the whole out of order execution buffer until everything is gone before that M fence, and then we can restart again and fill it. And so if you put a lot of these M fences, everything is going to grind to a halt. Yeah.
What's the difference between this instruction and the pause instruction?
The pause instruction prevents speculative execution. Speculative is with branch prediction. We don't even know that it's going to run in the future. Whereas the mFence guarantees about the retirement of instructions, like the order in which they actually get run. Okay, so let's take a look at this here. Let's see which one. Yeah, these are beautiful manuals, by the way. I highly recommend, evening reading. Oh, here's that list I wanted to do. Yeah, I didn't even talk about the instruction cache. There's a separate cache for instructions, but generally speaking, you don't change your instructions. You can. It's called self-modifying code. It's definitely not recommended. So the Intel chip, they keep a separate instruction cache and data cache. The instruction cache are just the instructions, right? And they're usually accessed in sequence. They're and they don't really change much. So they can build that a different way than the data cache, which is accessed all over the place and usually written to. Anyway, so that's a D cache versus the I cache. So running down here, so this, let's ignore that. But they didn't talk about the external last level cache, like the remote last level cache in this. Okay, I wanted to look at here. All right, so first we want to talk about what are memory accesses. The CPU accesses in a single instruction. It can make one memory access out of an 8-byte read or write. So if you have a wider one than that, there's no guarantee for the order within those bytes. In my experience, it also does wider than that, but this is sort of the standard that they provide. So I think I should make it bigger, right? How can I hide this? Oh, maybe. Okay, so here's some neat examples. So we know that the total store order is guaranteed. So I'm sorry, but this is, let's see, which one is which? I think this is Intel syntax, and GCC and everything we look at tends to be an AT&T syntax. So everything's backwards, and they don't have the dollars and stuff. So this is a store. And we're moving the number 1, it's not from the address 1, into this variable x. Okay, so what they're saying here is we start out with x and y being zeros. It's not possible that you would get, if you're reading on another processor, it's not possible, and that's also out of order here. It's not possible that you wouldn't get a 1. If x is a 1, then y has to be a 1 as well. This is good to know. It's actually probably the most useful part of the Intel memory consistency model. So here we're reading it out of order, right? So you could imagine, if this order wasn't guaranteed, you could imagine that the y finished earlier, depending on the cache state and stuff, in which case we might be able to see the 1 for y, but still get a 0 for x. That's not possible. The same is true for loads. So, let's see, yeah.
So in that previous example, we still don't know what state we're going to see x1, x, y in, except that there is this one state that's not allowed because they're in order.
Exactly, right. So we could get 0, 0, 0 naturally, because we can't synchronize in that tight. We could get 0, 1, but you can't get a 1, 0. And we don't get to, so if we load something, we don't get to finish our writes before the load. So in this case here, we wouldn't be able to get let's see. So processor 1 can't get a 1 from y because, if this is a 1, then y can't be a 1. That's the general idea. Okay. So this is for so you can't move stores above loads. You can't finish the stores earlier than the loads, but you can actually do your loads earlier than stores. So stores can kind of run before. And that's where we start getting some funny effects. And hopefully we can do a demo of that. Actually, I'm not sure. But then if you're writing to the So this is kind of intuitive. This is how it ought to be. So now we're writing a 1 to x, and then on the same CPU, this store hasn't finished yet, right? But we still get to read the current value, the 1 out of x, for our next for our load here. And the reason is, and this is for the same location, right? So if this was reading y, that could execute long before the store. But if it's the same one, then there's this load after store thing out of the store buffer that kind of saves us here. Otherwise, things would get really weird. So that one's really useful. Yeah. So things can appear in a different order on this CPU than on all the other CPUs, because we get to see our store sooner than, so in this case here, we wrote to X, and now we can read from X immediately. But processor 1 doesn't get to see, cannot do this load after store from our store buffer. So basically, processor 1 will potentially get a different order of the X and Y than we do, because one of them is local and the other one is remote. But if we were writing both X and Y here, the processor 1 would be guaranteed to see both stores at the same time. You can see how this is getting kind of tricky to get right. And generally speaking, it's better to use locking, right? Or to use something where you don't need to worry about these things. Sprinkle your code full of M fences and you're fine. Of course, it's going to run slow as molasses. Right? So the same is essentially true for locks, unless you're very careful with locks. Let's not worry about this one. Oh yeah, this one's really important. So here we have 4 processors. 1 and 2 are writing to X and Y. Sorry, 0 and 1 are writing to X and Y. And we don't know in which order. And that can be any order, naturally. But it's guaranteed that processor 2 and 3 see them in the same order. So processor 0 will see them in a different order than 2 and 3, because one of them is local. Right? 1 will see them in a different order, but these 2 will at least see them in the same order. So there's something. And this one's really crazy. So all locked instructions, no matter to which variable, have a total order. So one CPU over here tries to lock X, another CPU over here tries to lock Y, and processor 2 and 3, they see them locking X and Y in the same order. And I don't really know how they do that. That seems like really a lot of communication to coordinate that. But it's probably necessary to avoid deadlock. I think I'll just leave it at that. So, so you could imagine then, if you're doing a lot of lock acquisitions, that this communication, in order to perfectly order this with respect to all other CPUs, would also be quite a bit of overhead. I am not familiar with any counters that can let us measure this. And if you find some, major bonus in the class, because I want to see this data. But I don't know how to do it. Okay, and then loads and stores. So they don't get to go, you don't get to run instructions out of order with respect to locked instructions. Same as with an M fence. In fact, a little unclear on the difference between a locked instruction and an M fence with regard to this. I'll see if I can figure it out. Right. Okay, I think we'll leave it at that. Yeah.
Is this like a functional guarantee or like a behavioral guarantee? In the sense that like, it's gonna behave as though they're not reordered, but it still can?
Oh, yeah, that's right. So the guarantees are only about what can be observed. So it can do things. So for example, it might speculatively execute a load past a fence, and then just guarantee that load, as long as nobody else accessed it, and it somehow makes sure that nobody else wrote to it, then it might still be okay. It's hard to tell which one because it's not observable. But maybe with performance measurements again, you can come up with weird little benchmarks that somehow reveal the truth about these things. Okay, I promised that we would do some experiments. Unfortunately, this took longer than I thought it would. I'll put together a series of neat experiments for next time. And we'll spend most of the lecture on that.
Besides reading the manual, are there any extra resources for us to take a look at this? Some of it's a little complicated, might want to be revisited.
Yeah, I'll try to find some good resources. I think that this one is not so bad, just this part. So this is.
Can you post links to those?
Yeah, definitely. Do that.
Yeah, taking a look at these and trying to get this to see a little bit more, might be really good.
Yeah, it's hairy stuff. Okay, thank you very much, and I will see you on Thursday.
So how
No,
does it
Tuesday.
tell, like, how do they